Synthesis, Properties, and Characterization of Nanofluid, a critical review. Abstract. In last few decades, there is a remarkable number of researches that has been carried out on nanofluids and hybrid nanofluids because of its enhanced thermal conductivity and heat transfer characteristics. Heat transfer is a very important task that has to be carried out at regular time interval and at definite rates. Failing in it, which may result in a non-recoverable damage to the component. In order to achieve a better result, the use of nano-sized metallic or non-metallic particles with greater thermal conductivity than the fluid in which the particle is suspended have to be used. The liquid used to carry the nanoparticle is called carrier fluid or base fluid. In the present paper, efforts have been made to focus on various methods of synthesis of nanofluid and hybrid nanofluids, technique of stabilization, its common types and general properties of nanofluids and hybrid nanofluids employed in real-life application. Keywords: a nanofluid, heat transfer, base fluid, thermal conductivity, particle size. Introduction. Nanofluids are engineered colloidal suspensions of nanoparticles in a base fluid. Generally, the nanoparticles used in nanofluids are made of metals, oxides, carbides, or carbon nanotubes. Common base fluids include water, ethylene glycol, and oil. Nanotechnology is considered to be one of the important forces that could drive the next major industrial revolution. The primary method of nanotechnology is to employ the structure at the molecular level with the goal of achieving desired change in property with extraordinary precision. 1. The performance of the nanotechnology in diverse applications, which includes heat exchangers, biomedical, photocatalysts, and others. However, one of the major demands in the industry is the essential of an extremely efficient heat rejection mechanism to increase the overall proficiency of a working system too. Many researchers have worked by varying the concentration of the nano-sized particle in the base. Some researchers have changed the nanoparticle, few have conducted study by varying the base fluid, and few use the mixture of different types of nanoparticles to form a hybrid nanofluids used to understand the behavior of the fluid at various circumstances. It has been proven by some of the researchers that hybrid nanofluids show more dominant thermal and fluid flow properties than just nanofluids under certain compositions and conditions. 9. It becomes our bounded responsibility to understand the various types of nanofluids present, methods of synthesis, method of stabilization of nanofluids, and some of the important thermal properties before starting any research, and hence, an effort have been put to write a review on the same. Synthesis and preparation of nanofluid. The performance of the nanofluid depends on various factors such as concentration of nanoparticles in the given base fluid, size of the nanoparticle, dispersion quality, stability of suspension, stable chemical composition and non-corrosive nature of the nanoparticle with the base fluid, etc. In order to achieve this, the synthesis technique adopted plays an important role. One-step method. The process of preparation of nanoparticles is done by simultaneous creation and dispersion. Pulsed wire evaporation is the most promising method of single-step preparation technique, which consists of high-voltage DC power supply, wire feeding system, capacitor bank, condensation chamber, etc. In this method, a high-voltage pulse directed on a thin wire that melts and evaporates it within microsecond due to the effect of non-equilibrium heating. These vaporized particles made in contact with an inert gas such as argon or nitrogen inside the condensation chamber and condensed into nanosized powder. 21. In this method, the major problem is formation of agglomeration and its unsuitability to produce pure metallic nanopowders. The agglomeration problem can be reduced to better extent by adopting direct evaporation condensation technique. 1. Two-step method. In two-step method, the nanofluid are prepared by dispersion of nanoparticles into the base fluid one after the another, the prepared unitary nanofluids, and then mixed together, and synthesized the nanocomposite and then dispersed it into base fluid. 21. This method was employed for the preparation of mono and hybrid fluid by Hongwei Xian et al. 2. Firstly, distilled water and ethylene glycol were mixed in weightage ratio of a 60:40 as base fluid. Surfactant in 1:1 concentration of nanoparticles was added into the prepared base fluid and stirred for 10 minutes. COOHGNP powder was used to produce mono-nanofluid. For hybrid nanofluid, TiO2 and COOHGNP powder were mixed into the prepared base fluid with a 50:50 weightage ratio using a magnetic stirrer. Lastly, the mixture was sonicated again using a probe sonicator at 60% amplitude to disperse nanoparticles from agglomerating. This method is most economical and common synthesis technique for the preparation of nanofluid in large quantities. Because the nanopowder manufacturing technique have already started providing up to desired industrial level of production. 3. Ultrasonication. A two-step method was used for the preparation of nanofluid by using Al2O3 nanoparticles with an average diameter of 13 nm with spherical shape suspending in distilled water. 4. The advantage of this method is ability to control volume concentration. 9. Types of nanofluids. In this section, various nanoparticles used for the preparation of nanofluids reported by different researchers are discussed in details. Water/distilled water base A nanofluids. The commonly used base fluid for the preparation of nanofluid is water or distilled water, which is due to easily available in the market and economical. Ethylene glycol and distilled water were mixed in equal proportion to prepare base fluid. Carboxyl functionalized graphene nanoplatelets, COOHGNP, powders was used to produce mono-nanofluid. Titanium oxide and COOHGNP powder were mixed in the prepared base fluid for preparation of hybrid nanofluid using magnetic stirrer. 2. Alumina water and alumina iron/water hybrid nanofluids was used for the performance of flat plate collector. 3. Aluminium oxide water nanofluid was used to analyze the consequence of ultrasonication duration on colloidal dispersion and thermophysical properties such as density, thermal conductivity, viscosity, and microstructure of Al2O3 water nanofluid for different ultrasonication duration. 4. Titanium oxide distilled water nanofluid preparation was done to know the influence of surfactant and ultrasonic processing on improvement of stability, thermal conductivity, and viscosity. 5. Graphene/water, silicon/water and graphene silicon oxide/water hybrid nanofluid was prepared and evaluated for viscosity measurement, stability of nanofluid, structural analysis. 6. Different nanoparticles such as Al2O3 9, 11, 12, 14, 15, and 16, MgO, SiC, aluminum nitride, MWCNT18 and copper was used with base fluid as distilled water under different pH value for evaluation of heat transfer and pressure drop characterization, combined hydrothermal performances and entropy generation. 8. Synthesis of graphene silver/water hybrid nanofluids was reported for enhanced heat transfer. 17. Copper water nanofluid was prepared for heat transfer in the jet array's impingement cooling system. 19. Ethylene glycol base A nanofluids. A stable ethylene glycol-based silicon multi-walled carbon nanotubes nanofluid with mass fraction ranging from 0.01% to 1% was prepared to evaluate the unique properties of nanomaterials, stability of nanofluid, optical properties, and photothermal conversion properties. 10. Properties of nanofluids. In this section, properties such as thermal conductivity, density, viscosity, specific heat, and specific heat of nanofluid prepared by previous researcher have been discussed in detail. Thermal conductivity. Hybrid nanofluid prepared by using graphene nanoplatelets and titanium oxide with base fluid as mixture of distilled water and ethylene glycol resulted increasing thermal conductivity for all the samples. The maximum and average deviation for thermal conductivity was 3.12% and 2.57%. 2. Work on Al2O3 nanofluid for 0.5 volume percent of nanoparticles was done and reported that thermal conductivity was enhanced accordingly with the intensification of temperature. Brownian motion of nanoparticles increases due to higher nanofluid temperature and enhance the thermal conductivity. 4. With increase in temperature, the thermal conductivity of titanium nanoparticle with distilled water is varied linearly. 5. Mesoporous silica modified by copper nanoparticle hybrid nanofluid shows the increased thermal conductivity of 24.24% when compared with base fluid at a temperature of 50 and at concentration of 0.075%. 13. Increase in oxide nanofluid volume fraction shows increased thermal conductivity, particularly larger in ethylene glycol with CuO nanofluid when compared with water CuO nanofluid. 15. It is reported that graphene nanoplatelet sliver hybrid nanofluid exhibits increase in thermal conductivity with increase in temperature as well as increase in particle concentration. 17. Viscosity. For graphene nanoplatelets and titanium oxide with base fluid as mixture of distilled water and ethylene glycol, the average deviation of prepared hybrid nanofluid was 1.68%. It was reported that the prepared hybrid nanofluid obeys Newtonian fluids too. It was reported that the working fluid is also a significant factor that influence the thermal performance of flat plate collector. Al2O3 water nanofluids at a nanoparticle concentration of 0.1% exhibits a thermal enhancement of 2.16% in the collector, while reduction in thermal performance was reported for hybrid nanofluid of 1.79%. 3. Viscosity of nanofluid significantly decreases with increase in temperature from 10 to 50 for Al2O3 nanofluid for 0.5 volume percent of nanoparticles. The reason is due to weakening of interparticle adhesion forces with the increase of temperature. 4. With increase in temperature, the viscosity of titanium nanoparticle with distilled water is fell within the stated accuracy of the viscometer. 5. Viscosity of pure water at different temperature was measured and compared with the OSHRI handbook, shows that the measured viscosity is validated at all temperature. Graphene SiO2/water hybrid nanofluid at 25 exhibits decrease in viscosity with increase in shear rate, while increase the viscosity with increase in concentration of nanofluid from 0.05% to 1% and also when compared to pure water. 6. Viscosity was found to be decrease with increase in temperature for different nanofluid. However, for water the viscosity was found to be declined slightly and validated with the OSHRI data handbook. 9. With increment in particle volume fraction, viscosity of all types of nanofluids gradually increases, which is due to formation of clusters and internal viscous stress in the fluid, with the addition of nanoparticles in the base fluid. CuO/water-based nanofluid shows highest viscosity at each fraction when compared to Al2O3-TO2/water hybrid nanofluid. 12. Heat transfer coefficient. Greater enhancement of heat transfer coefficient was observed for Al2O3 water nanofluid and Al2O3/Fe water nanofluid, nearly 72% and 56% when compared with its base fluid respectively. 3. Heat transfer coefficient for Al2O3 carbon nanotube/distilled water shows the highest value when compared to water and Al2O3 nanofluid. When inlet temperature increases, the heat transfer coefficient also increase for different fluids. 8. Overall heat transfer coefficient increase with increase in nanofluid flow rate. However, for CNT/water nanofluid result in enhanced heat transfer when compared to water at two different heat section. 18. The suspended copper/water nanofluid can remarkably improve heat transfer behaviors of the base fluid, and heat transfer coefficient increase with increase in volume fraction of nanoparticles. 19. Density. It was reported that density of Al2O3 nanofluid for 0.5 volume percent of nanoparticles increased with increasing ultrasonication duration. This is due to at lower ultrasonication period, nanoparticles are not well dispersed. 4. Ternary hybrid nanofluid shows increased density with increase in volume fraction of nanofluid for Al2O3-TO2-CuO/water base. 12. It was reported that increase in particle concentration density of graphene nanoplatelet sliver hybrid nanofluid also increase at constant temperature, while density decrease with increase in temperature at constant particle concentration. 17. Specific heat. Decrease in specific heat capacity with increase in volume concentration for different nanofluid. When compared to hybrid nanofluid, the mono nanofluid shows increased specific heat capacity for the same concentration. Increase in volume concentration of ZNO hybrid nanofluid resulted in decrease in specific heat capacity at constant temperature of 25.9. Conclusion. Critical review on synthesis, types, and properties of nanofluid was discussed in details based on the previous researcher findings. Increase in temperature result in enhanced thermal conductivity for all the nanofluid while viscosity was decreases with increase in shear rate. Two-step synthesis process is preferable than single-step process for preparation of nanofluid, which is due to control over the volume concentration of nanofluid. Performance of mono-nanofluid is comparatively lower than that of hybrid nanofluid with respect to thermal properties. When concentration of nanofluid increases, the viscosity was found to be decline. However, viscosity of nanofluid can be improved for lower temperature when compared to higher temperature. Validation of nanofluid may be done by using OSHRI handbook. Future work. The base fluid may be prepared by using water and ethylene glycol with equal proportion. For the prepared base fluid, Al2O3 and graphene nanoparticles can be added to prepare hybrid nanofluid. Another set of hybrid nanofluid can be prepared using titanium oxide and zinc oxide with the same combination of base fluid. Further, comparison can be made on the prepared hybrid nanofluid. Acknowledgements. We gratefully thank to Visvesvaraya Technological University, VTU, Jnana Sangama, Belagavi for the support protracted to this research work.